What if you could use the power of computing to solve complex industry design problems? Many firms are embracing computational design tools for this purpose. With computational design and generative design, you can save time by automating repetitive tasks and iterate, analyze, and generate more sophisticated design solutions using simple data, logic, and analysis. Let's take a look at some examples of computational generative design using Project Refinery for the architectural industry. In this floor area ratio study, we're looking at a conceptual mass from computerized study in Dynamo, realized in Revit. Using the generate option in Refinery, we can run a dynamic FAR study that allows us to flex the plaza offset to show the geometric impact within the context of the site. Goals are set for outputs such as maximize total square footage, minimize facade area, minimize the number of floors, and minimize the floor variance. We're also able to adjust the population size for generations of the multi-objective optimization. When generated, the resulting study reveals a series of data-driven options with varying forms. We can make quick changes to our graphs to analyze data based on varying parameters, such as plaza offset or total square footage. Using send to Revit functionality programmed into the FAR graph, we have the option of pushing our final design to the Revit workspace and generating native Revit geometry within the Revit application from the Refinery workspace. This seamless data transfer from schematic design through design development, coupled with a truly responsive and informative design methodology, truly encapsulates the future of making. This Dynamo graph generates a residential tower and measures window-to-wall ratios, or WWR, and energy use intensity. In this residential tower optimization study, various sections of the graph control big picture elements such as tower height and floor quantities, building shell geometry, floor plate creation, facade section creation, and facade section tessellation. It is possible to make adjustments to key facade articulation elements such as floor heights, window-to-wall ratios, window bays, balcony sizing, and shading percentage manually in the Dynamo environment through the implementation of number slides in the graph. The goal of the graph is to maximize window-to-wall ratios and minimize energy use intensity. Using Project Refinery, it is possible to generate random options to test the script and understand the problem scope. You can see the Refinery server running in the background and the results are generated. Select results to set inputs in the Dynamo script and regenerate the model or run an optimized task to return new results. The results are visible in the principal component analysis graph and weighted with color to differentiate results. In this Dynamo graph, we are optimizing a curtain wall system by creating a panel fabrication readiness check. Our inputs are facade choice, number of vertical grid lines, number of horizontal grid lines, max planar deviation, and minimum internal frame angle. Our results to be displayed in fractal include max height, max width, max surface, plane deviation, internal angle, and custom panelization. With goals of minimizing maximum height, width, and surface, as well as plane deviation, internal angle, and number of custom panels, our study in Refinery is run with a population of 20 and a generation of 12. The results reveal an extensive list of possible systems and adjustments of X and Y axes of the analysis graph reveal a gradient of solutions that make more or less sense based on our initial goals. As an option is selected in the graph, the geometry is updated in the Dynamo preview and then may be sent to Revit for documentation. Let's take a look at some examples within the engineering industry. This graph generates a catenary shell in Dynamo and Dynashape and evaluates the rectangular and planary of the generated quads based on the position of the anchor points on the ground. The input parameters for the base point locations are driven by Refinery. The sections of the graph include the inputs for shape generation, Dynashape nodes for geometry, shape evaluation, and results. Code blocks populated with design script are used to define the points for the anchors and the goals of these elements. Defining certain nodes as inputs and outputs ensure that they will be considered in the Refinery environment as variables. Refinery launches the extension and inputs regarding the position of base points are defined for this study. Outputs attempt to minimize or maximize certain aspects of this catenary shell shape. The study runs with a population size of 48 and 5 generations using the optimized methodology. The refinery server runs and the results show a series of solutions to achieve the goals of the study. It is possible to choose a final design at the intersection of criteria visually for an optimized Catenary shell. This graph uses Dyno to optimize conceptual structural steel design. This is a diagrid structure for the Mars Torus concert arena. The optimization in the study is based on waste percentage, structure weight, total cost of the structure, including influence of tooling such as connections and beam cuts. The variables for the structure are dimensions such as the height of the torus and the division of the diagrid. Refinery is used to drive the three input parameters and to find the best solution for every generation. The first advantage of this method is that it only took about 80 minutes for 1600 runs. Refinery returns accurate design options where waste, total cost and structure weight are brought back to minimize values. This Dyno graph is conceptual evaluation of special truss design options and is used with Project Refinery for multi-objective optimization purposes. Inputs for the study are platform top edges, platform mid edges, platform width, platform length, truss start depth, truss end depth and truss segments. The results that we are using to refine our design ideas are deformation score, material score and platform area. In analysing the structure, it is possible to toggle the tube volumes for the structural members. In Refinery, inputs and outputs are defined with goals of minimising the material score, minimising the deformation score and maximising the platform area. The study is created with a population of 80 and with 10 generations. Toggling through the x-axis and y-axis values of the graph reveals the ideal solutions based on platform area versus deformation score, for example with a data point size driven by material score and a colour defined by platform length. Within construction, this crane optimization study evaluates the imported crane construction elements from Revit through SAT based on their weight and distance to a double tower crane setup. The calculation groups element per lift status and returns the total lift score for the situation. Building elements such as walls, floors, columns and beams are imported through SAT, and data references such as crane capacity tables are constructed at the beginning of the graph. The input for the optimization is both crane and truck positions, and the goals are based on lift score as well as time. Using the distance of the truck to crane and crane to solid centre point as indication of time and trying to minimise the time that crane is used for each installation. With a population size of 16 and a series of 10 generations, the resulting options show the scores for the crane positions relative to time and make optimal selections a simple task for the design study. In this parking garage optimization study, there are a series of inputs for the ramps, floors and structure as well as goals for parking space counts and an overall estimated cost of the structure. Using Refinery, we can test structural lengths and widths as well as ramp length and position to deduce the garage with the greatest return on investment. Design shift visually as options are tested. This study is highly relevant to this type of workflow as parking garages are highly constrained in terms of what is possible with design, as so are an obvious choice for automation with computational design and optimization with Refinery.